Good morning. Okay, let's finish the double integral today, okay? The midterm exam, I'm only probably 20 copies left, so, and then I need to record the marks, and so should be able to return it back next week, okay? Yeah, then I'll start 246. Lots of work. Double integral, okay? So we'll talk about the midterm when you get back to your papers, okay? And then overall, not bad, okay? So I got quite a few people got 100%, so that's very impressive, and then many got over 90. However, on the other side, there's still quite a few of you guys got maybe 20 or 30, so that's a striking difference there, right? We need to, yeah, I don't know what's going on here, and we need to basically shorten the gap here. Okay, given a function f x, y defined over a region R, okay, in the xy plane, okay, double integral is defined as basically this guy here. And so this is the notation of double integral. Okay, so what I'm talking about here is a purely mathematics thing. I'm not relating to any applications here, right? It's just purely definition. So double integral is this, and because you have two variables, so then you will integrate basically the dA at here is a small area in the region R. So you can either dx dy or dy dx, doesn't matter. Okay, so that's basically the definition. This is the definition. Then we'll have a lecture on the application of double integral. But overall, basically, what exactly is this function? What does this function represent? So that basically defines the application of this double integral. If this function defined as a height, right, in the 3D space, then you're looking at volume here. If this function defined as a density function, then this guy here will give you the mass of a certain plate. Okay? If this guy defined a certain temperature, then you get the overall temperature over a certain kind of area region R. Okay, so that's basically the depends on the meaning of fxy here. And we also went over the question in doing double integral. So here I'm going to talk about the detailed procedures, okay, of doing double integral here. Okay. Now, what you need to be careful here is this is a xy, so later we're going to talk about instead of xy, we're going to talk about r and theta. So at here, when we have xy written here, we basically call the Cartesian coordinates, right? So now we're talking about procedures here in Cartesian coordinates, okay? Okay, so what's the typical procedure? I'm going to use essentially an example here. Okay, so I'm not going to solve it, but we'll just lay down the procedure. First of all, if you look at this one here, you do double integral in the region R. So I'll give you the region R here. So the region R is is this kind of a shape right here. Okay, this is region R. and this part of the curve is x squared plus y squared equal to 1, and this line at here is x plus y equal to 1. Okay. So the region R is the area sandwiched between the two curves. Okay. And we're going to integrate. So this is R, and we're going to integrate this fx, some kind of function. Okay. No, we're not going to do a specific example. So we're going to integrate this certain kind of function, okay, over this region R. Okay. Yeah. So here's the procedure. Okay. Step number 1. Okay. Step number 1 here is what I just did here. Step number 1 is sketch this region R. Okay. So if you don't feel like sketching, that's fine. If you're confident becoming an expert here, but usually when you have this region R here, you have a pretty good idea of finding the mean and max, which is what we're going to try to show you here. Okay. So sketching essentially, like for example, this guy here, the question must be telling you region R is between this line and this part of the circle, right? So what do? You basically draw the line, draw the circle, and then look at this common area sandwich, okay, between these two here. Okay. So step number 2. Okay. Step number 2 is for you is you decide, okay, or determine. Okay. Determine the order of integration. Okay, determine order integration. Order integration, as we showed you last lecture, you can either integrate x first or integrate y first, right? Yeah, so that's basically the meaning in here. So I'm gonna show an example here. So let's say, for example, the order of integration sometimes matters. Okay, sometimes it saves you computation time, but it's the other order probably will be more complicated. Okay, so for this particular case, I'll show you here. I'm gonna do, so for example, I'm gonna do dx first. Okay, so let's say I'm gonna do this dx. I decided to do. What did I decide? Actually, sorry, I decided to do the dy first. Okay, so basically I wanted to integrate with respect to the y first. Okay, so if you want to do integration with respect to y first, okay, then there comes the specific steps what you need to do. So what we do is, in this particular case, you do the y first. You need to find the y limits. Okay, you need to find the y limits. So how do we find the y limits then, right? Okay, so the way to find y limits is, what you do is you draw, okay, you draw a vertical line. Okay, you draw a vertical line anywhere, okay, across this region R. Okay, so but just don't draw it here or here, right? You draw it somewhere in between, cross the region R. Okay, cross region. So for example, right here, we're going to draw it like this. So this is not vertical, but yeah. So that's you draw vertical lines like that, right? You cross this region R here. Okay. Then imagine yourself. There is a stick man here. Start to walk. Okay, the direction is always from bottom to the top. Okay, so always walking towards, okay, from the bottom to the top. So it's going to walk along the line here, and then as you're walking, and all of a sudden getting to contact with the region R, right? And keep walking, and be getting out of the region R. Okay. So there will be basically 2 contact points at here. Okay. So this is a simple region here. Okay. In this case, you're going to get 2 contact points here. So then for this particular case, okay, what our y mean, right, which is basically the limits that we're looking for. This is going to be the first, okay, first contact points. Okay, this is going to be the first first contact point. Okay. The first contact point between this stick man and the region R. Okay. And y max, okay, as you can imagine, that's basically your second, okay, contact point between this guy here. All right, so this is the line you draw arbitrarily across this region R vertically here. Okay, yeah. Okay, so in this particular case, as you can see now, okay, so where did I get in contact? I get in contact, it doesn't matter where I draw, I get in contact with this one here, right? Which is basically I get in contact with this line right here. Okay, yeah. So in this particular case, what will be the what will be the y mean at here? The y mean will be what? Y minus x. See, this is your line here, right? This is your line here. So doesn't matter where you cross. You know, whether you're here, right? You're crossing the line. So the line here is y equal to y minus x. Okay. Is that clear? Yeah. Then you look at the second contact point, which is this contact point here. This contact point is anywhere along this on this circle here, right? On this circle here. So this circle is defined by x squared plus y squared equal to 1. So that means y max would be, yes, right, square root 1 minus x squared, right? Like anywhere along this part of the curve here is square root 1 minus x squared. Okay, you don't need to the negative because you're right here, right? It's always positive here. Okay, yeah, is that good? So that's y mean and y max at here. Okay, yeah. Maybe I should also mention is you can think of it as y f of x somewhere. Okay, I'm just drawing the region R here, right? But you're integrating this guy here. This guy is actually somehow on the top of the region R here. Okay, yeah. So that's how you find the y mean and the y max. Okay. So then the next step is to find this x limit. Okay, it's x limits. So the x limits. X limits is you have this vertical line at here, right? You have this vertical line. So let's say I have this vertical line at here, right? Yeah. So then what you do is you basically sweep this vertical line, okay, across this whole region R, okay, horizontally. So across them. When you're sweeping through them, you find the absolute edge of this line and the region R. So the edge, and in this particular case, one is over here, the other is over here, right? Yeah. And that edge corresponding value, or the x value of the edge, is the x mean and the x max. Is that clear? Yeah. So remember the concept what I was describing in the last lecture. Integration is about what? Integration is about the sweeping. Basically, you need to cover every corners, right? So the first choice you did is you draw the line here. Basically, you create, this small segments here. And the second step, what we're doing, we're sweeping. Basically, we're trying to sweep the whole through this whole region here. So you're not gonna leaving any empty space of this region R. You're integrating from, within across this whole region R here, right? So that's the second step here. So for the finding the x limits, okay, sweep the vertical line, okay, across R. Okay. Find, okay, the edges or boundaries. Okay, find the edges or boundaries. The corresponding mean and the max of the boundaries is x mean and x max. So in this particular case, okay, my x mean and x max, if I look at this one here, where's my x mean? X mean must be here, right? So that means x mean is 0. X max must be here. So my drawing is not that accurate, but it's a circle. So basically, if you draw a line, vertical line here, that circle will be tangent to the circle, to the line, and the intersection between this vertical line and the circle right here, the x value must be 1. Right? Must be 1. So your x mean is 0 and your x max is 1. Okay. This is another thing you got to be careful is when you choose the order of integration, the last one that you're integrating. Okay, this is second order, so this double integral. So this second one is x. The last one must be constant. Okay, the integral limits must be constant. Okay? The first one here, the limits could be a function of the other variables. Okay, not necessarily a constant. So this is basically the mean and the max, and then overlay, right? Your double integral, right? This is x mean, this is x max, y mean, y max. You're doing y first, then x. So that means I can put down my limits at here. So my y here is 1 minus x to root 1 minus x squared, and x goes from 0 to 1, right? 0 to 1. So that's the double integral you're looking at. If the function fxy is given, and you can carry out this double integral fairly easily here. Okay, yeah. Just make sure that you consider x as a constant when you're doing this integral here. Right. Okay. Any questions? All good. So why don't you try the other way around? What if you do dx first? Okay. What if you do dx first? What will be this x mean? What will be x mean x max, y mean y max? Here is this r here. Okay. So if you do x first, according to our procedure, what do? You draw instead of vertical line, you draw a horizontal line here, right? Then you look at this first contact point and second contact point, right? And that'll be the x mean and x max. So x mean and here will be, what's that? That's right, 1 minus y, x max. Okay, this guy. And then y mean, you sweep this line across this whole region, okay, and find the boundaries, okay, to sandwich this region R. So y mean will be 0, y max will be 1. Okay, yeah. So clear? Okay, good. So that's all this, basically just follow steps, okay, follow the steps, and you should be fine. Okay. Now let's take an example here. Okay. Okay, let's take this is a simple one here. This is quite simple, I think. Okay. So I'm telling you that R is a region bounded by y equal to x, x equal to 1, and x-axis. Okay, so y is the region of this. Then I have a function fxy, which is this guy here. Okay, so that's basically a kind of plane in here, right? A plane. And let's try to find the volume. Okay. Okay. Try to find the volume below this function f and above this region R. Okay, find the volume below this f and region R. So the first step, right, is to sketch this region R. So quite simple sketch. So what do we have here? We have two straight lines here, right? Got two straight lines. And then there's x-axis. So y equal to x, which is what? This one here. And x equal to 1, which is this. Okay. And x-axis, which is this. So the region R you're looking at is, right, it's this. And you're looking for the this volume of this one. So in 3D space, it would probably look like this now, right? In 3D space, this is x, this is y, and y equal to x is a line, something like this, and x equal to 1, which is this. So here is the region R here, right? Here's region R. Okay. And the function z is this, 3 minus x minus y. So that's a plane, right? That's a plane. So the plane, this is z. The plane will more or less look like what? 3 at here. With z equal to x, you also go to 3. So the plane will more or less look like this is 3. So yeah, I'm drawing. So more or less look like more or less look like this. Okay, so on the top of it, basically, it's an inclined plane. Okay, inclined plane, and which will somehow intersect this xy plane at here. Okay, yeah. And my hand drawing is going to be hard here, but anyway, so try to visualize that. All right, yeah. But even though you can't visualize, okay, the mathematics is still very simple. So what do? We do basically integrate this guy over this region R, right? Over this region R. Okay. All right. So first step you sketch, then the second step you choose an order of integration, right? So I guess which one do you want to choose? You want to integrate the y first, right? Let's say we choose dy first. Okay. If I choose dy first, according to my steps, what do? I draw a vertical line. Okay. I draw a vertical line pointing up. Okay, because that's where I'm going to walk my stickman there. Okay, so draw it anywhere arbitrarily across that region R. Okay. Then the first contact point give me the y mean. Second contact point give me y max. Right, give me y max. So then y mean in this particular case, it doesn't matter where you draw. Y mean is always what? 0. And y max doesn't matter where you draw. It always hit this top boundary y equal to x. So y max is x. Okay, it's x. And the second step, sweep this line across this whole region R. Okay, find the bounds. Okay, for this vertical line, x bounds. So apparently one is over here, one is over here. So x mean is 0, x max is 1. Okay. So at the beginning you want to write a few words at here, right? But once you're getting comfortable, you can directly jump into this double integral and start to calculate. Okay. So in my particular case, I find the mean and the max. X is 0 to 1, y is 0 to x. We're integrating this guy here, and we're integrating y first, then x. So that's this layout of the double integral. Okay, yeah. And this is a quite simple integration at here. Okay, so let's try it out. In the middle here, integrating with respect to y. Okay, I think I need to mention one thing here. Notice a lot of you guys, when you do integration, right? So you write 0 to 1, 3t squared. That's it. And technically speaking, that's not an integral, right? Yeah, don't forget this. Okay. So there are many of you guys write like that. I'm not sure. Is a first year teacher do that, or high school habit? Okay. Yeah, if you are doing a rough calculation, it's fine. But when you write things properly, you need to have that down variables there. Okay. So middle one here, integration 3y xy minus 1/2 y squared. From where? From 0 to x. Okay. Yeah, by the way, I do also notice there's a couple of things, calculations you missed a point here. You know, I see some student do this integral 18, let's say, plus t squared, right? dt. So they start is equal to 18 t squared dt. So that'll cost you dearly because you know you get everything right, but right here, right? Yeah. Oh, by the way, that's not right, huh? So coming back here, the middle one here, 0 to 1. Okay, 3x minus x squared minus 1/2 x squared, and when you plug the 0 to y, everywhere is 0, so that's just this one thing here. And the integral here, I think you can practice this, and overall you end up with a 1 in here, okay? You end up with 1. So which basically means the volume between that surface, okay, and the region R is 1. Okay? Yeah. So you can try the other order if you do dx first, and what will be these results? Of course, it's going to be 1 again. Just try it out yourself. Okay, one more example. Okay, now this is a tricky one here. Tricky not in terms of finding limits, tricky in terms of calculation here. Hang on a second. Before we talk the other one, this is the other kind of application here. I give you the double integral. Okay. So I give you a double integral here. Then I may ask you this question here. Here's a double integral. I want you to sketch the region R. Okay. So the question didn't say anything about region R. It gave you a double integral. It asked you to sketch. Yes. Yeah. Oh, 2x. Sorry. Okay. Yeah. So how would you sketch the region R? How do you get the information region R based on what? The bounds, the limits at here, right? So that's another type of question here. So how do you get the information? You need to basically go back to the procedure that we just presented here. When we're presenting the procedure, it's about how to find the min and max, right? And the min and max is basically showing it here. And how do we find the min and max? In this particular case, you're doing the y first. So this is y min, this is y max, this is x min, this is x max. Which means what? Which means you draw the vertical line, and the first contact between the vertical line and the region R is y equal to x squared. And the second contact between this vertical line and the region R is y equal to 2x, right? So basically, you can think of, oh, I'm going to draw a vertical line. And the first contact is y equal to x squared. So, okay, let's draw y equal to x squared, right? Y equal to x squared is something like this. That's y equal to x squared. So it doesn't matter where I draw, well, that's the line there, right? And the second contact is y equal to 2x. So you draw the 2x there. So y equal to 2x is going to be probably something like this, right? This is y equal to 2x. So basically, I guess the vertical line you draw probably not going to be here, right? Not going to be here. If you draw it here, the first contact is not this. It's going to be this guy here. So it's going to be over here. This is the first contact, the second contact. Okay. So that actually tells you pretty much this R now, right? So your first contact is, then you look at the area sandwiched by the two curves. That's basically your region R, right? And you can now go back to the x min, see if that makes sense now. The x min here is the bounds, okay, of the vertical line, okay, bounding this R here, which is 0 to 2, and 0 is over here, so that intersection point must be 2. Is that going to be 2? So you can solve these equations, y equal to x squared and y equal to 2x as 2, right? So this point here is 2. Is it 2? No. X equal to 2 is 4, is 2, 4, right? It's 2, 4. So y equal to 4, x equal to 2. Okay. So that's basically the region R here, okay? Yeah. Doesn't matter how complicated this function here is, okay? Just use the same technique, okay? and try to sketch. Of course, somehow you have to be able to sketch that, and then you'll be able to find the region R. Okay. The purpose of doing this one here is, the purpose of doing this is, in particular, maybe you don't want to do Y first. You probably want to do X first, right? Probably want to do X first. So in that particular case, if you don't sketch this region R, it might be difficult to find the proper X mean and X max, right? But once you have the region R now, let's say I wanted to integrate with respect to X first. Then following the procedure that we presented there, so what do? We draw horizontal lines, right? We draw horizontal lines and find the first contact and the second contact between that line and the region R. That'll be my X mean and X max. So let's say, for example, in this particular case, if I do dx first, then first contact's here, second contact's here. So tell me what's the first contact, what's the X mean now? Right, what's X mean? That's right, y over 2. Right, first contact is this line here. So x equal to y over 2. Then x max, how about x max? It's this curve, which is basically x equal to, that's right, square root of y. Okay, yeah, not negative, positive. Okay, and then find the y mean and y max, which is the bounds of these horizontal lines. So starting from 0 to that point, which is 4. Okay, is that good? Okay, so that way you lay down the same double integral, but now the order is changed. Okay, so this is your new double integral. Okay, yeah, you should have the same results, of course. So you tried it, and the result here is 8. Okay, any questions? Yeah. How did I find a 4 here? No. Oh, how did I find a 2, 4 here? This is the intersection point between y equal to x squared and y equal to 2x, right? So basically, okay, so you solve the two equations. Yeah. Okay, so try that. Another example. Okay, so this is the one I'm talking about here, and my region R is this. Okay, so notice the different way of describing region R here. Okay, yeah. So this is region R, and let's see my fxy equal to y squared. And I want you to calculate the double integral, okay, of this function y squared. Okay. First step, what do? We sketch R, right? Okay, sketch R. Okay, understand what this means here. Okay, first for in this region R here, first condition x squared plus y squared less than 1, less than equal to 1. Well, if equal to 1 is what? It's a circle, right? It's a circle. If less than 1, less than or equal to 1, meaning where is it? It's inside the circle, right? Yeah, inside the circle. So basically it's a circle inside a circle here. And the second condition is x greater than 0, y greater than 0. Basically that constrains your region R at where? At the first quadrant, right? The first quadrant here. So here basically this is your region R here. Okay. Yeah, the other thing is, you know, from now on we're gonna do a lot of things. The sketching is a very essential skill. For example, sketching a circle, sketching a sphere, a parabola, a paraboloid. Okay, yeah, those kind of things. Okay, a cone. Okay. Yeah. All right. So this is a region R, and then let's try to let's say I'm gonna do dy first. Okay. And do dy first, meaning you draw vertical lines up. Okay. First contact give you the y mean. Second contact give you this y max. Right. Okay. and sweep this line here, you end up with the x mean and x max. So I'm going to skip myself a little bit. So x mean is 0, x max is 1 because the radius is 1. Okay, and y mean here is 0, and y max is the top point at here. That top point is defined by the circle, and that's root 1 minus y squared. Okay, just like that example we went over there. And we're integrating y squared, so which is dy and dx like this, right? Oh, sorry, this is x here. Okay, so nothing strange, nothing different from previous example. Okay, but then here comes the challenge at here. If I carry out the integral inside here, okay, carry out the integral here, let's see what do we have. This is y squared, so that's 1/3 y here, right? And then going from 0 to root 1 x squared, that's what's inside there. So if I plug this one here, what do I get? I can pull out 1/3 out, and root, okay, 1 minus x squared cubic here, and dx. Okay. Okay, so looking at this one here, I think that probably will feel most of us here, this integral. That's actually, as a matter of fact, if I get away from this for a while, I won't be able to do this either. So this basically is not a very integral to do, right? However, you really want to do that, so generally you use substitution. Okay, x equal to sine u. Okay, so let x equal to sine u here, and then dx will be just cosine u du. Because x goes 0 to 1, then you plug in this for the variable u, and u will go from 0 to pi over 2, right? So that's the basic steps of substitution. Then this integral here, okay, will become 1/3. Back to the blue line here. It will become 1/3 here, 0 pi over 2. Right, we're going to integrate it with respect to u now. Cosine u cubic here, cosine u du. Okay, is that clear? Yeah, that's substitution, right? So this inside here, this is cosine u to the power 4, right? This is cosine u to the power 4. Right? You let sine u, y minus sine u squared is cosine u. Square root of cosine u give you back this cosine u here. And this is to the power 3, so to the power 3. And dx is cosine u du, so this portion is dx here, right? Dx here, okay? So this one here, you know, I don't think this is an easy example. I do have a formula here. I'm not going to write it, actually. It takes a while to write it. So this is basically a fairly difficult integral here. Because why? Because we are, you know, using what coordinate? We're using x, y. This is Cartesian coordinates here, right? Yeah. So with this typical procedure here with the Cartesian coordinates, okay, that just turned out to be very challenging integral here. Okay. So I'm not going to do this. Okay. And the question is there a better way of carrying out this double integral instead of using these Cartesian coordinates, right? Yeah. So I think you probably said it. It's what? Polar coordinates. That's right. So this is our next topic here. Double integral, okay, in polar coordinates. Okay, in polar coordinates. Okay, so first we need to understand what a polar coordinates is. Cartesian coordinates is x and y. So polar coordinates, given the same point x and y, the polar coordinate defined as this. You draw a line from here to here, then the magnitude from there to the point is r. The angle, okay, from the horizontal axis to where this vector, or you call the line, whatever, and that angle is called theta. Okay, so the theta is always defined. Okay, remember theta is always defined from the horizontal axis to where it is. Okay, that's theta. So polar coordinates meaning r theta here. Okay, r theta. Okay, yeah. Okay, and the relationship between the polar coordinates and the Cartesian coordinates is actually quite straightforward. So if you look at this, this is your x here, and this is your y. So we have actually done this quite a few times. So what's the x here? The x equal to r cosine theta. What's the y? Y equal to r sine theta, right? Okay, so that's the relationship between polar and Cartesian coordinates. All right. Okay, so we got the relationship here, and let's go back to our double integral. Here is the definition of a double integral here, right? This definition of double integral. So we said we're not going to integrate this thing, or we're not going to calculate this thing using Cartesian coordinates. We're trying to do it using polar coordinate. So which means what? Which means we're going to replace this x and y here with what? With this r cosine theta, r sine theta, right? So that's easy to understand, okay? Okay, so we're going to replace this x with r cosine theta, replace the y with r sine theta. Okay, so then there comes the question, what about this dA at here? Okay, so originally the dA is dx, dy, or dy, dx, doesn't matter, okay, right? Okay, so first impression is, but it's a dangerous one, you don't want to try that. It's okay, if this is dx, dy, maybe I'll just try dx here, dy, and replace that with dx, dy, right? Yeah, that's the first, but we cannot do that, actually. Turn out that's not a good, that's not the right way of doing it. So essentially, the right way of thinking of this one here is, this dA in Cartesian coordinates is this, okay? dA in Cartesian is this. So the whole point here is, how about this dA in polar coordinates, right? Well, how do I approximate a small area A in polar coordinates? So over here, you approximate a small area using this dx, dy, the rectangle here, right? Similarly, if I have a small area, what will be this dA in polar? So there will be a r and theta somehow here, right? Yeah, so that's what we need to figure out here, okay? So what we do is, I'll draw something in here to show you this general approach here. Okay. So let's say what I have here is a certain kind of region like this, right? Certain kind of region like this. And when you have a Cartesian coordinates, the way we do the approximation is you cannot dissect this certain kind of area using horizontal lines and vertical lines, right? Then you have many small rectangles, right? So let's say now my area is not really a sort of a rectangular kind of shape, maybe a circular kind of shape, okay? So then what I'm going to do is I'm going to dissect my this r here with this. I'm going to draw many clustered, okay, curves like this, okay? Many clustered this. And also I'm going to draw some reading lines, you know, out of this origin and here. So similarly, now you can see now this region is kind of dissected or divided into many what? Many these small areas, right? Many small areas. So imagine what you're doing, right? Imagine what you're doing is, let's say if you draw as many of these circles here or many of these reading lines as possible, and each one of this, well, they're not a rectangle, but when you draw as many possible, each one of them actually is pretty much still like what? Rectangle, right? Still a rectangle. Okay, so I'm going to single out one of these out, single out one of the rectangle here, but exaggerate that a little bit. Okay, yeah, and so we're going to draw something like this. So let's say, suppose that we have a certain, okay, kind of a area, okay, sandwiched by two curve and two reading lines. Okay, yeah. And we're using polar coordinates, right? Polar coordinates. So suppose the first line here is giving the theta. And remember what you're doing is you're approximating. So every line, the theta between every two lines are pretty small. So the second line to the first line here, this angle here, okay, so I'm going to call it delta theta. Okay, delta theta. Okay. Yeah. And for the first inner circle here, let's call it R. Okay, let's call it R. Okay. And the second one here, okay, So second one here, there's also a circle right here. It's also has radius. So this is going to be r plus delta r. So basically, okay, this small distance here is delta r. Okay, it's delta r. So that's all I need. Okay, that's all I need. Okay, what I'm trying to find is I'm trying to find this area, which is the dA. Okay, the dA here. Okay, we're trying to find the area. So as we said, you know, we have so many of the lines, reading lines, so many of the curves. So I'm going to think of this, okay, small area as a rectangle. Okay, rectangle. So which means the area is going to be basically the area or the length of this multiplied by the length of this. Okay, yeah. So in other words, this is actually a curve, right? This is actually a curve, an arc, but we think of it as a straight line here. Okay, a straight line. So what's this? What is the? If I use now before I use the d, let's use the delta here. The area is this length multiplied by this guy here, right? Multiply this. So this guy is delta r, so that's good, right? That's easy. Right? This is delta r here. How about this arc length here? That's right, r delta theta, right? R delta theta. Right. Okay. Now this is delta a here. We're talking about dA. So what do? Just change the delta to d, right? To d here. So dA is r dr d theta. Okay, dr d theta. Now we have the same dA, and in terms of the r and theta now. Okay, yeah. So it's not just dr d theta. It's actually there's an extra term r at here, right? Yeah. Is that good? So then this double integral here, I'm going to replace dx dy with what? With r dr d theta. Okay. So basically, my new double integral, okay, yeah, is rf r cos theta, r sin theta, r dr d theta. So that's my double integral in polar coordinates. Okay, in polar coordinates. Any questions? Yeah, yeah. So far so good. Yeah. So do you just have to somehow remember this? I think the best way is just to remember this one. That'll be enough. Okay. Yeah. Okay. So we went over the general steps of doing double integral in Cartesian coordinates. So we draw lines, right? You know, vertical lines, horizontal lines, doesn't matter. So let's take a look at the same approach here. What will be the general approach of doing double integral using polar coordinates? Okay, yeah. So let's take a look at general approach here. And I'm going to use a sample region R, okay, to carry out these general procedures. Okay, so here's this region R here. Okay, so this is the region R. The bottom here is y equal to root 2. The top here is x squared plus y squared equal to 4. Okay. Yeah. Okay, so that's it. That's the region R. Okay, so we're gonna remember we're gonna use the polar coordinates. Okay. Yeah. When you do polar coordinates, you also determine order. Okay, but usually you do this R first. Okay, you usually do the R first. So usually you do dr first. Okay. So then let's see, if I do dr first, what's the general way of doing this? Okay, so what do? Is you draw a reading line. Okay, draw a reading line basically starting from origin. Okay, from origin. Okay, across region R. Okay, across the region R here. So what does that mean? That means basically you starting from origin here, okay, and draw a reading lines like that across this region R. okay, across the region R. Okay. So when you do that, right, inevitably you will have certain kind of contact points between that reading line and the region R, right? And so essentially you can still think there's a guy walking, okay, from origin outwards, and you have a first contact point, you have a second contact points. Okay. So similarly here, first contact, okay, first contact gives R mean. Okay, first contact gives R mean. And second contact gives R max. Okay, gives R max. Is that clear? Okay, so let's take a look at what's the R mean and R max that are here. I think I'm gonna let me see if I need to. No, I don't have to. Okay, so let's look at this graph here. Right? Let's look at this graph here. Maybe let's find R max first. R max is easy. Okay, so it doesn't matter where you draw. The second contact is always where? On the circle, right? On this circle. So what will be the R max value? 4. Radius here is 2, right? So R max is 2. Okay, it's 2. So then back to the R mean. R mean is what? See, always remember, huh? R max is basically from here to here, the distance from here to here, right? That's R max. And R mean will be the distance from where to where? From here to the first contact points. So R mean is the value from the origin to the first contact points. So R mean equal to distance from origin to first contact. Okay, first contact. Similarly, R max is distance from origin to second contact. Okay, yeah. Okay, so now let's get back to the R mean here. First question is R mean going to be a constant? No, right? Because if you draw the reading lines over here, the R mean, the distance changes, right? So it's not going to be constant. So then the question here is, can we find an expression for the R mean, right? It's not an arbitrary expression. It's going to be an expression based on the geometry at here, basically. Okay, yeah. So this is R mean we're talking about. I guess it doesn't hurt to put down the theta. Okay, let's see what's the theta. Theta is always in polar coordinates. Theta is always defined as the angle from the horizontal axis to where the line is, right? That's theta. Okay. How do I find this R mean then? Okay. Vectors? What?
Hypotenuse, like 2 squared plus x squared.
2 squared plus. Okay, so you're thinking, yes, good. So I'm not sure what, but I guess what you really want to do is, I guess you want to, if you want a geometry here. I don't have all the information here, right? So maybe let's look at this, some of the geometry here. What is the value over here? Root 2, good. And what would be the value over here?
4.
No, 2. What about this value here? This point. What about the coordinate of this point here? Root 2, excellent. Okay, so I think that's all we need here. Okay, now we're looking for this distance, right? Looking for this distance here. So let's try and look at this one. Look at this triangle here. Okay, look at this triangle. So what's that triangle? That's the triangle here. Right, this triangle here, okay? What's this side here? The length is root 2, right? Root 2. So we're looking for this distance. This is R mean. Okay, this is R mean. And where's the theta? Theta is over here. This theta here, right? This theta. So which means this angle here is theta. So can you tell me what R mean is now? R mean cos theta equal to what? Well, cos theta or maybe sine theta. Okay, R means sine theta equal to root 2. So which means R mean equal to root 2 over sine theta. Okay, so that basically is R mean, right? R mean is a function of theta, right? That's perfect, you know, because that's what we need. You know, we don't want R mean in terms of x. We don't want R mean in terms of a y or anything else. You know, because we're doing using polar coordinates r as theta, so that's great. Okay, so then that's R mean now, right? And this is basically draw a reading line across this region R. Okay, from the first contact and the second contact point from R mean of x. Okay, then what you're gonna do is the next step is to find, right? The next step is to find theta limits. Okay, theta limits. So finding theta limits is what you do is you do this. This is the reading line that you draw it here, right? So what you do is you rotate this reading line. Okay, rotate it. Okay, not moving it, not just rotate it. Rotate it across this whole region R. Find the bounds. Okay, the corresponding theta bounds. Corresponding theta bounds at the two edges for this region R. So in this particular case, where's my first edge is here, right? My second edge is here. And at this edge here, I have a theta mean. And at this edge here, I have a theta max. Is that good? Yeah? So I guess I'm going to look at this specifically, okay, the case like this. Okay, so here is this region here. So the first bound is here. The second bound is here. Okay, second bound is here. So this angle here is theta mean. And then this angle here is theta max. Okay, it's theta max. So let's see the easy one. What's the theta max? Pi over 2, right? How about theta mean now? Right? Huh? Tan. Do you really need a tan here? So this line passing which point? Passing this point here, right? And we figure out the coordinate of this point is root 2. So which means, what's this value here? 45. Right? Or pi over 4. Okay, pi over 4. So once these two steps done, your most challenging work is basically solved. Okay, so we basically just need to lay down the double integral. Okay, you're integrating a certain function f here, so r cos, r sine, and r dr d theta. And in this particular case, my r goes from this is a mean here to top 2. Theta goes from pi over 4 to pi over 2. Okay, pi over 2. Okay, that's it. That's the typical approach, okay, of solving a double integral under polar coordinates. Okay. Yeah. You don't want it? Oh, it's okay. Go pick it up. Yeah. Okay. So let's look at an example here. So we're going to solve that particular challenge example, okay, from that previous question there. So what was that question? That's y squared there, right? Okay, I used a different one, but anyway, okay, let's try it. Okay, so here's that particular one there. Okay, let's try to solve this guy here. Okay. Okay, so first step, figure out this. You can lay down here actually. Okay. You have the sketch already, so it's a quarter circle. It's a quarter circle, and what we do is the first step is to figure out the R min R max, and to figure that out, we draw a reading lines out of this origin. First contact between this reading line give us R min. Second contact give us this R max. So guess what? Where's the first contact points? Yeah, exactly 0. And second point is over here, so that's 1, right? Okay, so everywhere is 1. And we're integrating, that's R min R max. And the theta is you sweep that guy, okay, across the whole region R, and you always start from 0. In this particular case, the first theta is 0, second theta is pi over 2. Okay. And we're integrating y squared, so we're going to replace the y with what? With r sine theta. Okay, r sine theta. And the dA needs to be changed into r dr d theta. All right? Yeah. Okay, so that's all it is. Okay? Yeah. Then let's carry out this integral here. We're integrating with back to r first, so the theta, sine theta here, you're going to consider as a constant, right? And there's r squared by the r, so it becomes r cubed. So I actually can pull that sine theta out of here, okay? So this is r cubed. And the inner integral here is r cubed here is 1/4 r, 4, right? Yeah. Oh, square, yes. Good point. It's all good? Oh, pi over 2. What's going on here? Okay, good. Thanks. Any more? Huh? Oh yeah, pi over 2 here. Yeah. Okay, I think that's it, right? Okay. So then this is the result. So integral so goes from 0 to 1 and d theta, right? D theta. Okay. So this guy here, I guess, just give us 1/4. D theta. Okay. So how do I do this guy? Sine theta squared. What was that formula again? The plus 1 minus 1. 1 minus this. Cos 2 theta is cosine theta squared minus sine theta squared, right? And 1 is cosine theta squared plus sine theta squared. Yes, it's 1 minus this. Okay? It's 1 minus this. So we're going to replace this sine theta squared with replace that with 1 minus cosine 2 theta over 2 d theta. Okay, d theta. Is that clear here? Yeah. So this integral is not that bad. This integral here, there's 1 over 2, that's a constant. The other is negative cosine theta over 2. And you can use a simple substitution. If you don't want it, you can try my method, right? So 1 over 2 here, 0 to pi over 2, 1 over 2 d theta, plus 0 pi over 2, 1 over, this is cosine 2 theta over 2. I'm going to change the theta to, I'm going to change the d theta to d2 theta. So then I need to divide it by another 2. So that'll become 1 over 2 here, right? So to keep it equivalent. So then the second integral here, the first integral is 1/4 and 1/2 multiplied by pi over 2 plus this is 1/4, okay, cosine 2 theta d2 theta, which give us what? Sine 2 theta, and goes from pi over 2. Okay, and the second one here, actually, when you plug the theta in here, 2 by pi over 2 is pi, sine pi is 0. Sine 0 is 0. So this whole thing is 0. You only have this first one there, and that should be for 14/16 pi over 16. Yeah. I have a minus. Oh yeah, my minus, sorry. Yeah, this is minus, right? Okay. Not quite myself here. That good? Okay. So that solved this one here. So now you can see, if you compare the calculation here involved with the calculation under Cartesian coordinates, and I guess I'll prefer this one here, right? Yeah, this is basically doable. Okay. The only catch is, of course, you probably need to know this guy. Okay. All right. Any questions? Are good? Yeah. Let's try one more example. Okay, so I have this region R at here. Okay, it's a half donut. So, yeah, lunchtime. So then I'm gonna find, what do I find? I try to find this one here. Okay, try to find this double integral. Okay. Okay, so when you have this kind of double integral here, I guess I forgot to mention one thing here, right? You got, now you have two different coordinate system, and instead of first you choose one, what to do is actually you need to choose which coordinate system you want to carry out this double integral. And in general, okay, when you have a circular kind of a bound, okay, then you probably want to use these polar coordinates. Okay? Yeah. Not necessarily always like that, but when you have a circular bound, okay, this polar coordinates is probably going to save certain computations. Okay. So coming back here, I decided to use a circular. I decided to use polar coordinates. Okay. So then the first thing I'm going to do, I'm going to figure out this R min, R max, and theta min, theta max, right? Okay. So following the procedure. So what do? We draw a reading line, okay, anywhere, okay, out of this origin here, okay, across this region R. Find the first contact and the second contact. These two contact points will give us this R min and R max. In this particular case, the first contact is here, second contact is there. So the R min should be A. R max would be B, right? Yeah. So R min is A and R max is B. And the theta min is you rotate these reading lines across this whole region R. Okay, find the bounds of the theta, okay, for this region R. So in this particular case, theta mean will be 0 to pi. That's right. Okay. Okay, so that's all it is. Then we can write down this double integral in terms of polar coordinates, theta 0 to pi, r from a to b. Change the y to polar coordinates. Change the dA to r dr d theta. That's it. Right. Okay, so this is also a simple integral even compared to previous example there. Sin theta, you can take it out of the inner integral there. And inside here is just r squared. Yeah, a lot of time I find some students forgot to multiply this r here. Okay, so let's be careful there. Okay. And this is essentially more or less like multiplicative of two single integrals. See, you carry this out there, or you can the d theta can move there, so it doesn't matter. So the overall is quite simple. So just 0 to pi sine theta. Inside here is 1/3 b cubed minus a cubed d theta. Okay, and the sine theta integration from 0 to pi give you 2. Okay, so that basically gives us 2/3 b cubed minus a cubed. Okay, b cubed minus a cubed. Yeah. Is that clear? No. See, okay. That equal to negative cos theta 0 to pi, right? So that equal to negative cos pi minus cos 0. And that equal to negative 1 minus what? 1, right? Negative 2, negative 2. And by the way, that actually does jog my memory here. You have no idea how many people made a mistake in the 248. You know, one of the point is, I think 1, negative 2, 3. And the other point is 2, negative 3, 5, right? So you're trying to find the vector between the 2 points. So this is P1, let's say P2. So P1, P2, right? And use this value, subtract this value. So that's what? 1, negative 5, 2. Lots of you, no, not that lots, but many of you made this kind of mistake. What should be here? Negative 1, right? Negative 1. Yeah. See, the worst thing is, this one is wrong, and you have absolutely the right idea doing the rest of the work, and they're all wrong. So, you know, yeah. What am I supposed to do? That's basically a very difficult position, huh? Yeah. So you got to avoid this kind of mistake. Okay. Yeah. Negative. There's somehow. Anyway. So any questions? All good? Okay. Yeah, we still got a little bit of time here. Just quickly finish a couple of the properties, okay? Yeah. So some of the common properties double integrals. Number one is, some of the properties are very much similar like the properties of single variables, okay? If you have a constant multiplying it here, you can take the constant out. Okay? Yeah. So that's called constant multiple. If you have double integrals of addition and subtraction with another one, and you can carry them separately. All right. Okay. Okay, so that's two simple one there. Okay. And the other property is this. If your fxy is greater and or equal to 0, okay, over this region R, then your double integral, okay, is also greater and equal to 1. Okay. So that's actually quite visualizable, because if you think of this double integral as a calculation of volume, okay, think of it as a calculation volume, and you have a surface which is greater than 0, right? Greater than 0 meaning every z value is greater than 0, and your region R is over here, and you're trying to find a volume, absolutely the volume will be greater than 0, right? Yeah. However, if this function is not always greater than 0, if this function somehow, part of the function sitting, okay, below this xy plane, then when you calculate the volume, it's not necessarily going to be greater than 0, right? Yeah, just like the single variable function. When you're integrating a curve like this, you're calculating area underneath the curve. If this part of area is bigger than this part of area, then you get a negative value, right? Yeah. And similarly, if you have this guy less than 0 over R, then that particular one will be less than 0. Okay. And the last property is this, additive property. Okay, so if you have integration here, and the R happen to be, okay, composed of two regions. So for example, okay, you have one region over here, one region over here, and then you have another region somehow over here. This is R2, this is R1. No, I'm just not a 3D, just XY plane, okay? Okay, like this. Then all you need to do is you can separate this double integral into two regions, okay? It's basically like a single integral here, right? Okay, like this. Okay, same idea. So we're going to practice one example of this in the next lecture. Okay, any questions? Okay.